So this paper is about faster algorithm for minimum cost flow for sparse graphs. It's joint work with Aleksander Mądry and Adrian Vladu. So let's first define the problem. We have a graph and we're given a demand vector, and we're looking to find a flow that satisfies this demand, meaning that the net flow through each vertex is equal to the prescribed demand on that vertex. Additionally, we want to satisfy some capacity constraints on each edge. Here's a flow that satisfies those. And finally, among all such flows, we want to minimize the cost. So for each edge, we have a cost, which is for each unit of flow, how much we pay for this flow, and we want to minimize the total cost. So this is a flow that satisfies all of these constraints and also minimizes the cost. So what is known? This is a very old problem from Dinitz's 1973. But in 2008, there was an M23 halves algorithm from Deitz and Spillman that used interior point method. And until now, this has been the best known algorithm for sparse graphs. For dense graphs, the LP solver of Lee and Sidford improved this to M root n. So our work gives an M23 halves minus eta time algorithm, and this is the first one to break the Deitz and Spillman bound for sparse graphs. And if you're curious, eta is 1/762. So let's first give a quick summary of interior point method for flow problems. This is the mean cost flow linear program where we want to minimize the linear cost function under a demand and capacity constraint. And to solve it with interior point method, we replace the capacity constraints by logarithmic barrier terms in the objective. These logarithmic barrier terms blow up when these constraints are close to being violated. And in particular, if we look at this parameter mu and plot all the different optima of this objective for different values of mu, it gives us the so-called central path in the polytope. And if we are able to trace this central path, we will end up with the optimal solution to the LP. In particular, in each iteration, we're given the optimal solution for mu, and we decrease mu by a little bit and want to find the optimal solution for the new value of mu. And we can also write this optimization problem in terms of the change in the flow f tilde, and an even more drastic simplification is to take a second order approximation, and so we end up with a quadratic. And this is an electrical flow problem. It's not, of course, it's not equivalent to the original problem, but it will allow us to make a step. Now, in each step, in terms of flows, what it does is it pushes an augmenting circulation to the flow in each step. In particular, after scaling down the flow, it pushes an electrical flow to maintain the fact that the demand should be fixed. And slightly abusing notation, we will just ignore this scaling part and just call this electrical flow f tilde. So one thing we know about this is that it has low energy. So its energy is bounded by delta squared m. And in fact, what this can tell us is that the energy of each individual edge has also a bound. And if we know that the energy of each individual edge is bounded by, let's say, 1/2, then we know that the capacity constraints are not violated. So a delta large enough so that the capacity constraints are not violated gives us a good enough step. And in particular, the standard setting here is setting delta to something like 1/√m. So this automatically implies that the capacity constraints are fine and gives √m iterations. But in particular, what if we have a stronger bound in the energy of some edge? And the nice and interesting thing is that if we have this edge that has a low energy over a number of steps, then we know that for only 1 over epsilon steps, this edge is not interesting. So it will, okay, its flow will change, but not change by a significant amount. So this means that there are some edges that we can ignore and some edges that we can't. So that's why it's important to look at the energies of different edges. In particular, here is the canonical example of where we have a high energy edge. So the edge on the top here gets half of the total flow. So it has a high energy. And so how do we fix this problem? So one approach that has been very successful is to try to perturb this edge in order to reduce its flow by either deleting the edge or increasing the resistance of this edge. So somehow artificially trying to reduce the flow of this edge. And this actually corresponds to changing the weights in the log barrier terms in our objective, or equivalently changing the trajectory of the central path. And this has been shown that it can reduce the number of iterations of the interior point method. And Leon Sidford and myself, Mądry and Vladu, and from 2020, have the state-of-the-art results using this framework for a bunch of problems where we showed that it's m to 4/3. There is a runtime of m to 4/3. Now, there's also another approach we could take, which is instead of trying to change this edge, try to focus on it and reduce the runtime of each iteration instead of reducing the number of iterations. And this is an approach which was started by Gaolu and Peng, which they also have a talk about it in this FOCS, and they reduce the runtime of max flow below m to 3/2. So instead of reducing the number of iterations, we reduce the time it takes to solve each iteration. So this is actually, if we take a closer look, it's related to dynamic electrical flows. So because the problem is we need a data structure that can find the solution to an electrical flow, an approximate solution, fast. And in particular, we have a graph with dynamic resistances and dynamic demands. And we also have a couple of conditions, which I will not describe, but come from the interior point method. And we would like to return a flow that the error of this flow on this edge is at most epsilon times the energy. And the way we measure the error is we measure the energy of the difference between our flow and the optimal flow. So this is the problem we would like to solve. And in fact, we show that we can do this in sublinear time as long as the various problem parameters are small enough. So now let's look at, let's go through the key ideas in our work. The first one is demand localization. Basically, it says that we can have a demand on n vertices, but we can actually project it down to a sublinear number of vertices without losing basically anything as far as high energy edges are concerned. The second one is demand stability. Well, as the algorithm progresses, the set C here that is on which the demand is supported will change, but we show that when C changes, the demand doesn't have to change for quite a few iterations. So if we keep the demand the same, then we can still detect high energy edges. And finally, energy localization, which is saying that we can look at the neighborhood around C, which we call epsilon important edges, and only search there for high energy edges. So let's start with the first idea. And here the goal is to prove or to see when we have some demand, let's say here is an ST, and we push this demand towards C, so we project it on C, does this lead to any high energy edges while this is projected to C? And in general, this is true. For an arbitrary C, this is true. In particular, here for a single edge, the energy can be as large as 1/m on this edge, which is not bad. But if we have L of these edges, then this might be as large as L²/m, which is pretty bad. Because L can be M, can be all of the edges in the graph. Fortunately, we can show a much better bound. In fact, it relates to the heating probabilities starting from these demand pairs to C and E. So it's the probability of reaching E before reaching C. And if we're able to show that the sum of these probabilities is small, then we're in good shape. And in fact, this is possible. By picking C in a careful way, we can prove that the sum of these probabilities is bounded by some parameter dependent on the size of C. And so as long as C is large enough, there are no high energy edges before the demand reaches C. In other words, we can project this demand onto C without creating any high energy edges. Now let's go to the second part, which is the demand stability. Again, what happens is that as resistances change gradually, and C will change as well. It will include more and more vertices. So when it includes a new vertex, the demand will have to be updated, because remember that the demand is a projection, so it depends on C. So here, in particular, the demand should change, but let's actually see what is the error of not updating the demand. And let's look at the specific edge and what is the energy of this edge because of the error in demand. So in particular, the energy of this edge is at most the total energy of this demand difference, the difference between the old and the new demand. And we can also do something similar with the previous idea and bound this by some heating probabilities. For each demand pair ST is the probability that it reaches V before C. So it's a bit different, but again, some similar probabilities. And for the same reason as before, we can bound it by a nice quantity. So again, we proved, so now we proved that even after polynomial number of updates in 1/epsilon, the effect of the demand on the energy is just to multiply it by 1 ± epsilon, which is a negligible change. So we can make many updates, but still the effect of the change in the demand is tiny. So what this means, what these two facts combined mean, is that we can first localize the demand on a sublinear subset, and then we can just keep it intact for just for a polynomial number of iterations. Finally, the energy localization. So first of all, we have these demands in C, and what we want is, first of all, we would like to compute the potentials that these demands induce. So we use the vertex sparsifiers of Durfee, Gagorans, and Peng in order to find this, to maintain these potentials in C. But now we'd also like to find all high energy edges in sublinear time. So even after having these potentials, it's not clear how to detect high energy edges fast. This has been solved, actually. One can use sketching, which I will not go into detail here, but the point is that this can be done. And the part I will concentrate on is if I have a single edge that I want to estimate its energy by taking some random walks to C, then how many random walks do I need to do that? So again, I will not go into details, but using this result, we can get detection for all edges. So let's fix this UV pair here. And in fact, what is known is that this phi u, potential of at u, we can estimate it by taking a number of random walks where probabilities are given by inverse resistances from u to c. And the error, what we show is that the error in the potential is bounded by, there is an epsilon there, which is good, but it also has a dependence on the effective resistance between u and c. But this is the bound that we get, and we conclude that with 1 over epsilon samples, we can get such an approximation in the potentials. We'll see in a second whether it's good or bad, but it depends on the effective resistance between u and c, which is the electrical distance between u and c. The way this bound works is it's in a concentration bound that takes into account the fact that the energy of phi of the potentials is small. Okay, so now we do the same for V, so we estimate both, and we want to see what is the error in the energy of the edge, UV, that we estimated. So the error, what we show is that it's at most epsilon times a ratio of resistances. On the numerator, we have the effective resistance we talked about, and on the denominator, we have the resistance between U and V, the resistance of the edge UV. So this actually is good whenever the edge UV is close to C relative to its own resistance, but it's really bad when it's very far from C. So how can we deal with this? In fact, what we show is that if we look at radius around C, which we call epsilon important edges, in fact, more precisely, these are exactly the edges that we can sample from. So the edges that are outside of this set have low energy. So in other words, for each edge, either it is an epsilon important edge, so it lies in the outer circle in this shape, and we can sample, we can efficiently estimate its energy, or it lies outside of this circle, and we don't care about its energy because it's too small. So that's the idea here. And this way is this way we localize all the high energy edges in this outer circle that we know we can find them efficiently. To conclude, we gave an M2 faster than M2 3/2 time algorithm for mean cost flow using interior point method. And the main tool was data structure to solve dynamic Laplacian systems under some special circumstances. So L infinity error instead of L2, and resistances and demands change smoothly. And we also had the certificate that the demands can be routed with low energy. Thank you.